Last episode, we found that decode wastes the GPU and that batching is the cure. Pack many users into one weight read and you get throughput almost for free. So, why can't we just batch everyone? Because two old habits waste enormous memory and stall the GPU. How the Kavi cache is stored and how requests are grouped. Fix both, and this is where the real speed lives. On-screen hook, two fixes turn wasted GPU into 3 to 5 times the traffic. Spoken callback, we said batching saves decode. Now we remove the two things, fragmented memory and static batches, that were stopping us from batching enough. First waste, memory. The old way reserved one big contiguous block of Kavi memory for every request, sized for the longest answer it might ever produce. So a request that writes 20 words still holds a reservation for 2000. Most of it sits empty, and you run out of room for new users while the GPU is barely half full. That is fragmentation, and it is pure waste. The fix is the oldest trick in computing. Do what an operating system does for RAM. Stop demanding one big contiguous block. Chop the Kavi cache into small fixed size pages, 16 tokens each, and keep a little table that maps each request's words to whichever physical pages it actually got. Hand out pages only as the answer grows. Reclaim them the instant it finishes. Memory waste nearly disappears, and now around 90% of your Kavi memory is doing real work. This is paged attention, and paging gives you a gift. If two requests start with the same text, the same system prompt, the same few short examples, the same long document in a RAG app, those identical leading pages can be computed once and shared. The model prefills the shared part a single time for everyone. For RAG and agents, where every request carries the same big context, that is a huge cut in time to first token. Second waste, how we group requests. Static batching is a bus that won't leave until every seat is full and won't stop until the slowest passenger gets off. So, a one-word answer that finished instantly is stuck waiting for a 1,000-word answer to complete. Continuous batching replaces the bus with a conveyor belt. Finished requests step off, and new ones step on at every single decode step. The belt never stops, the GPU never idles. NVIDIA's engines call the same idea in-flight batching. Let me show both fixes on one diagram. Top half, memory, contiguous slabs versus paged blocks. Bottom half, scheduling, a static batch versus a continuous one. Watch the wasted space turn green and the idle lanes fill in. The old memory layout, one long contiguous slab per request, reserved for the maximum length. The actually used part is small, the rest is red, reserved, empty, wasted. 2 or 3 of these and you are out of memory, even though most of it is nothing. Now paged. The same sequences, chopped into 16 token blocks, scattered wherever they fit in a block grid, with a block table on the side mapping each request's logical positions to its physical blocks. Almost no red left, around 90% utilized. The same GPU now holds far more concurrent sequences. And the prefix sharing bonus. 2 requests arrive with the same opening blocks, the shared system prompt and document. Instead of 2 copies, both block tables point at the same physical blocks computed once. A copy on write flag means the moment their text diverges, they split. One prefill, many requests. Now scheduling the timeline view, static batching on top, 4 lanes, all forced to wait for the longest one. Big red idle bars where short requests already finished but can't leave. Continuous batching on the bottom. The instant a lane finishes, it drops out and a queued request slots in every step. The lanes stay full, the idle bars vanish. The clearest picture of why this is 3 to 5 times faster, and it is marked vendor reported. 2 inventions, one result. KV memory goes from 40% use to 90%, and the GPU stops waiting for the slowest request. Together, 3 to 5 times the traffic on the very same hardware. One honest footnote, Triton's older dynamic batching is a different, weaker thing. It groups whole requests before a single pass. Great for fixed shape models, wrong for one token at a time LLMs. For LLMs, you want this in-flight batching. And these two tricks are not loose code, they are baked into real engines. Next, the serving onion, vLLM, TensorRT-LLM, Triton and NIM, plus one more latency trick, speculative decoding. Thanks for watching. Like and subscribe for more videos like this, and I'll see you in the next one.